So today's lecture would be on multivariable control for robotic manipulators. Okay, so in the last two classes, we were dealing with control strategies for robotic manipulators. However, in those cases, each joint was considered separately and a single input, single output sort of control was being designed. And another important thing was that the coupling effects were ignored or basically considered as disturbances to the individual systems. However, the actual robotic manipulator is more complex. It is not actually linear system. There are non-linearities in it, and it is a multivariable system. So now in this lecture, we'll start the formulating the robot control problem as a multivariable control problem rather than a single input, single output problem, or a set of single input, single output problems. Okay, so just to recall, we had considered that at each joint of the robotic manipulator, we had considered we have the manipulator dynamics and the dynamics from the motor and gear train. This we had seen earlier too. However, in order to equate everything together and in order to get everything in terms of tau k and qk, we use a small arithmetical adjustment, and that is we multiply the second equation, that the equation of the motor and the gear train, by this factor of rk, and also take into account that the motor angle and the joint angle or the joint variable qk are related by this relationship. And when you substitute that and you integrate this equation, you write this equation, the second equation turns to this one. Okay, and now since both of them are have tau k on the right hand side, we can equate this term. Okay, we can write this term here and write and eliminate tau k in the middle, and so what we end up with is an equation that looks like this. Okay, and now this is an equation where all these terms are at each joint. So this is still in terms of each of those joint variables, and however we can write these equations in matrix format. So you have n equations. If it is an n link manipulator, then you will have n such equations, and you can write all those equations in a matrix format, where now m, c, b, this g and u are matrices. M would be an n cross n matrix, C again would be an n cross n matrix, B would be an n cross n matrix. This is an n cross 1 vector, and U is another n cross 1 vector. Okay, so you have something like this now, and just to explain the terms again, this M of Q is the same, is the diagonal matrix of J, which was this one, plus the inertia matrix that you got from the manipulator model, that is the Euler-Lagrange model of the manipulator. Okay, and the C is the Q dot times Q dot, represents the centrifugal and Coriolis effects. This was one of the major components that was considered as a disturbance in the independent joint control. And to compensate for this disturbance, we had in the computer torque control, we had incorporated this effect as a nonlinear control. So we were trying to calculate, we're trying to figure out what was this C of q comma q dot, and we gave c qd as an input, as a part of the input. Okay, so in this lecture we will try to say that is there a simpler solution, while so is there a simpler control than the computer torque control that does not ignore the Coriolis force and still gives performance. So is there a simpler controller structure than the complicated control of computer torque control that does not ignore the Coriolis and the centrifugal forces, does not consider them as disturbances, however gives a good performance, and doesn't have an error that is proportional to the magnitude of these effects. Okay, now the other terms that you have are the gravity term g of q. U is actually the input, is a vector of all the inputs, where Vk is the actual voltage that you're applying to each of the motors at each of the joints, and B of q constitutes it's a diagonal matrix indicating the damping factor. For now we are assuming that B is equal to 0. Okay, we are assuming that this B is equal to 0, and that the reason for that is because we assume that there is adequate lubrication and in the bearing. However, we will later try to figure out if we can you can incorporate B or not assume B equal to 0 and still guarantee the performance. Okay, so but for now, for the initial state, we are assuming that B is equal to 0, and let's see that how the things proceed. Okay, and like in the independent joint control, we had at each joint you had a control that was that had a proportional term which depended on the error between the joint and the desired joint position, and another term that was the derivative part that took care of the joint velocity. Okay, now in the multivariable case, we are using the same concept. Okay, and now if you however you have this Kp and Kd as matrices and n cross n matrices, where this Kp and Kd matrices are diagonal. So it basically is the same format of a control. However, the independent joint control can be written as diagonal matrices if you in a multivariable framework. A it should be noted that Kp and Kd not equal to diagonal is a choice that is available in multivariable format. However, that doesn't happen at all in the single variable in the independent joint control format. What it means is that while I am calculating UK in the independent joint control, we had said that it only depended upon Q, K tilde and Q dot. Here UK can depend upon other joint variables also. That sort of a flexibility is there if you go for independent joint control, if you try to use independent joint control for the control purpose, for the control design purpose. Okay. Okay. Now, for the purpose of the control design in multivariable PD, we first assume that the gravity term is 0. Okay, we assume that g of q or g is equal to 0. So if g is equal to 0, then and u is assumed to be of the PD structure, then you end up with this equation. What you end up with is actually m of q dot q double dot plus c q dot into q dot is equal to u. Okay, and you having this structure would give this equation. Okay, and what we want to prove is that the error, that is q tilde, goes to zero asymptotically with the same control, with the same diagonal control. Okay, and so it is a better proof for the stability. Okay, because now we are not assuming that the disturbance, that is the c q comma q dot, we are not assuming it to be a disturbance, we are not assuming it to be a constant also. Okay, now let's go further. So this is what we mean by the terminology asymptotically, that is, as the time tends to infinity, the error tends to 0. Here it stabilizes, so the response goes to some steady state value as error tends to 0, and that is what I mean by using the terminology of asymptotically. And while to prove the stability, to prove that the control of the structure Kp q tilde minus kd q dot, that is going to give me a stable, that is going to assure that the error goes to 0, we use the concept of Lyapunov stability. So in Lyapunov stability, what we basically do is that we formulate a Lyapunov function that that basically represents some sort of energy dependent on error. Okay, so this energy is equal to 0, or it and if this energy decreases, it indicates that the error is decreasing. So v of t decreasing for increasing t will assert that there is stability. So if, and this also is, as I said, that it is, this acts as an energy. V is something like an energy, or it acts like a norm, and that the norm decreasing, the value of v decreasing, would mean that the error is decreasing. Okay, and this is a pictorial representation of the concept of the Lyapunov function. So here in our case, what we have is are there only two variables that we will consider, two types of variables actually, not actually two variables. So the position and the velocity of the joints. Okay, and what we want is that the position should go to the q desired and the velocity should go to 0. This is the desired variables. Okay, and what we want is, we want to construct a function that is greater than 0 at all points except at this point. At qd 0, it should be equal to 0, and it is not equal to 0 or greater than 0 everywhere else. Now if I say, if we are able to assure that v dot is less than 0, okay, at all points except this qd0, then what we are effectively saying is that the trajectory is moving towards this point, towards the point qd and 0, because this has to, the magnitude has to decrease, so it is going towards that point. That seems to be a obvious conclusion, a natural conclusion out of that. Okay, now as we said that we want to make a Lyapunov function that is positive, that depends upon the velocity and the position also. So let's take this Lyapunov function, for which what we have to assume is that m of q is positive definite and this kp is also positive definite. So it just means that the mass matrix uh, assures that X transpose, or not even X transpose, we can say that Q dot transpose M of Q dot is greater than 0 whenever Q dot is not equal to 0, and Kp Q tilde transpose Kp Q tilde is greater than 0 whenever Q tilde is not equal to 0. This just means that this M and K are positive definite matrices, and that is something that is again quite simple to understand. And this term is in a way that this represents some kinetic energy of the robot. So you want the robot to have no no redundant kinetic energy when it reaches the desired position, and the potential energy is some sort of a potential energy term is represented here in the second term, and it's a pseudo potential energy because this potential energy is zero only when the robot is in the desired location, and it is non-zero, it is positive elsewhere. So this potential energy term can be only positive, not negative. Okay, and v is a positive function at all points except at the goal. At the goal, it would be 0. Okay, and now the aim next is to show that this v would decrease to 0 along any motion of the robot, and if we are able to show that it decreases to 0 when the control that we are proposing, the control of PD control structure that we are proposing, if that is applied, and the conclusion would be that if I are able to prove that v dot is less than 0 at all other points, then the conclusion is that the robot is moving towards the goal configuration. Okay, let's see. So we want to prove what is v dot. So when you want to show v dot and we take the time derivative of v dot, we end up in this situation where we may have to calculate what is m dot and we may have to calculate what is q tilde dot, because for the potential energy part you had q tilde, and if you go back you would see that in the potential energy equation you have q tilde, so you may have to compute what is q tilde dot, and in the kinetic energy equation you have m of q, and when you take the derivative with respect to time of for v, then you may have to compute what is m of q, the derivative m dot q may be needed. Okay, so but m dot q is the same as d dot q, where d is the inertia matrix that we get from the Euler-Lagrange equation. Okay, and so m dot q will be d dot q, because m of q is just d of q plus j, and j is a constant, and similarly q tilde dot will be minus q dot. So going further, you see that when you take the time derivative for v, you get this equations. Okay, so q dot transpose m of q dot, when you take the time derivative, actually half of this, when you take the time derivative, you will get something like q dot transpose m of q double dot, because you're taking the derivative with respect to q, and you have one term where it is m dot is actually d dot, and finally you get these three terms present in the terminology for v dot. However, by substituting for m of q double dot into this equation, the term simplifies to half of q dot transpose times this term d dot q minus 2c q comma q dot, okay, and minus q transpose k dq dot. So one thing is that if we are able to prove that this term is 0, then v dot will become minus q dot transpose k d q dot, something that cannot be negative, so that cannot be positive, because if we choose kd to be a positive definite matrix, then it would mean that this term at maximum it is 0 when q dot is 0, but it cannot be negative. So that is one thing. So what we need to do is that we need to prove that the term in the highlighted term, that becomes 0. Okay. Now the claim is that this term, that is d dot minus 2cq comma q dot, is actually a skew symmetric matrix, and that is why q dot into the skew symmetric matrix, q dot transpose skew symmetric matrix into the q dot, this would be equal to 0. Okay, this will be equal to 0. So let's see the proof of it. Okay. Okay, so if you see the inertia matrix for a robotic manipulator and take the time derivative of the inertia matrix, of course, if you have dkj, the time derivative of the inertia matrix is a summation of these terms. It's a summation of partial derivatives with respect to qi and qi dot. Okay, and if you see the expression for the terms in the Coriolis matrix, the Coriolis matrix is defined using the Christoffel symbols. Okay, so Christoffel symbols of first kind. Okay, and so this is Cijk, and from that you can get the Coriolis matrix, and what you end up with is, when you try to compute the kjth element for this difference, okay, you end up with this equation. Okay, however, if you look closely, you would see that since the inertia matrix is symmetric, dij is tji and dik is dki, and so nkj can be reformulated to be written in this manner, which is minus njk, which would mean that this n matrix is skew symmetric, as we had claimed. Okay, now what is the implication for this? The implication is that this is 0, means this the first term is 0, giving v dot is minus q dot kd q dot. However, this means that v dot is actually equal to 0 for q dot is 0. It's not q tilde is 0. So it is at any point where the velocity is 0, v dot is 0. So v becomes constant at any place where the velocity is can be consistently kept as 0. Okay. But this seems to be a problem because velocity can be 0 even when position equal to 0. Okay, so what we have is v dot equal to 0 means that q dot and q double dot, all of them are 0. Now let us say that, but the equation of motions were this. Okay, let's substitute q dot is 0 and q double dot 0 in this case. So what you end up with is that kp q tilde is 0. However, we have assumed, even while formulating the Lyapunov function, we have assumed that kp is a positive definite matrix. So even more basic than positive definite matrix, for kp to be a positive definite matrix, kp should be invertible. Okay, since kp is invertible, kp into q tilde equal to 0 would imply that q tilde equal to 0. Okay, so what we have is q tilde equal to 0, which means that q is equal to qd is the only point where v dot can be maintained at 0, which would mean that, and it is v dot is less than 0 at all points, okay, other than q equal to qd. Okay, so it converges to q equal to 0, q equal to qd. Okay, now until now we have ignored the gravitational term, and if you add the gravitational term now, if you add the gravitational term without changing the control, what you end up with is that instead of v dot being equal to 0, v dot being equal to just q dot kp q dot, you end up with v dot being equal to this expression. Okay, now what this would mean that after application of the PD control, v dot equal to 0 when this happens. So instead of q is equal to qd being the point at which it settles at an offset error where q minus qd, it settles at a location qd where kp into q minus qd is equivalent to the gravity term. So this can be interpreted in a manner, the physical interpretation can be that the motor generates a steady state holding torque, which is kp times this thing. Okay, that will compensate for the that will balance the gravitational torque. So let us say if I want to keep the manipulator in certain position, there is gravity acting in this direction. So there is, and so however I want to keep it in actually in this position. Okay, so to counteract gravity, it has to give some force, and that is why, and because it is giving that force, but it is not taking into account, if error was 0, it would not have been able to give any counteracting force. So now to maintain this steady state position, it has to give some torque, and to have that torque you need some error. So like the case where you only had this PD controller and without the integral part that we had, so without the integral part, when you had the case of the independent joint control PD controller, now too you have the case where there is a steady state error in when there is a gravity term here. Okay. However, as the case that we had with the independent joint control, here too the steady state error can be reduced by increasing the magnitude of the proportional control kp. Okay, and alternatively, it can also, the gravitational term can be incorporated into the control also. Okay, this seems to give, theoretically this will solve the problem, it will go to 0 steady state error. However, However, the downside is that this would require the computation of your gravity term g of q at each instant of time. So this would need some computational, maybe you need a microprocessor to compute on board the gravity effect at each instant of time. Okay, so this is like the computer torque control. But now the advantage of the over this control is, in the computer torque control you were actually using the Coriolis term itself. You had to compute the Coriolis term itself for the compensation. Here we have proved that in the multivariable case, merely having kp greater than 0 and kd greater than 0, or kp being positive definite and kd being positive definite, is enough for compensation, as long as the gravity term is not too large. If the gravity term is large, then an approximate compensation of the gravity term is also good enough to reduce the error, and a larger value of the proportional controller kp also helps in reducing the error. If the error has to be completely eliminated, one thing that has to be done is to actually use a nonlinear controller which computes g of q. However, that would require a lot of computation power. Okay, and the same logic can also be applied to nullify the damping part. Okay, so you can have a damping coefficient b of q dot incorporated in the response. So similarly, this will also take into account the damping effect, which we had ignored to be 0, and that also improves the performance. Okay, and with that we come to the end of this lecture. Okay, thank you very much.